Uh, okay. Um, so what I was telling you is that I did want to share, like this, like assignment stuff for, you know, for some coding. So let's see. I'll share my Firefox. I'll share this desktop. Uh, Stop share, or actually not. Let's share. Let me see what I want to share. So yes, yes, yes. Okay, I want to share this one. Okay, now you see this. So just a couple of things that I posted um over the weekend. Where do I have this? Let me see if I zoom in. Oh, okay. Yeah. So I had posted it as an assignment. So I made this assignment. Uh, with like so that you can try kind of like try to play a little bit with like this SVD decomposition. So what I was telling you is that okay for many of the things once we kind of like try to use some more like algorithms with tensor networks, there's this tensor library that I had mentioned you before, which is like where are you? iTensor. Okay. And they do have like a version of it that runs on Julia, if I'm not mistaken. So I thought like, oh yeah, this is like the recommended version. So just because like this one will use Julia, I think it would be a useful idea for you to download Julia, so that you can get some experience with that. And now I'm getting spam calls. And then there was like has been a very weird day because someone jumped on the path train. So like everything was canceled and it has been like a complete mess. So like it's like a black swan day. Okay, so then okay, just to go back to the assignment, like what I was saying is that if you go to I haven't made it an official deadline because I wanted to discuss it first with you so that you kind of like see where it all is. Right, so you can, if you want to download Julia, you can download it here. Um, I mean, for this assignment, you can use Python or whatever you feel more convenient, comfortable with MATLAB as well. But I think down the line, Julia would be a useful thing for you, also you to experiment. So you should download Julia. Uh, if I can do it with the help of GitHub Copilot, you can as well, because I know nothing. So like, okay. And then there's this thing also to run it kind of like in a more visual setting, like so which I also recommend on the assignment. So like you can click on it if you want to download it, which is again what I'm using as well to play with with it myself. Um, and then as I told you, like I really like this one. It's so fun. I also like a lot there. Find it very funny. So I mean, you don't have to do this, but also the coding that it involves is pretty simple. But what I like about the GitHub Copilot is that literally you just enter the prompt and it will spit out the code for you. An alternative to that, and like if you want to kind of like, I do want you to kind of like explore for yourselves a little bit of how to write it down. But if you kind of like look at the assignment, I kind of like suggest like some of the like yeah, the quality is not too good like here, but when you read it, it will look better. But like I kind of like suggest some prompts of how you could like get the code like for the assignment. Now, what is the assignment? So the assignment is like very like simple. It just has two parts. The first one, and let me see if I can show you that as well. Where do I have my so first part is you take a picture of something in the real world. So this is my picture. So just my cat showing her bust. So like that is my picture. Okay. And the idea is that we want to compress that assignment. Okay. That not that assignment, that picture. Okay. So Okay, the first thing, let me see. How is this called? Here you are. Okay, so the first thing is that, just for you to get acquainted with it, kind of like to create like a code where like the input is like an image, and then it spits out the matrix that corresponds to that pixelated image. So let me see if I have it here. Uh-huh. No, not open folder, but no, I don't. Wait, but no, nothing is working. Okay, for some reason, like, okay, oh my God, yeah. But okay, now, but this is not how I should, okay, okay. Okay, yeah, I guess, for some reason, uh, let's see if this works now. Allow. Like, now it has data, access to all my data. Like, yes, like, whatever. Um, Yes, like this is like weird bit. So okay, so for example, the idea is like the idea of the code is that the input would be an image, and it will spit out a matrix, and the entry on a particular like each of the matrices, like the matrix entries would become like the value in a grayscale, like of like of the corresponding image. So like you can have it like go from like depends on how you write it. It could like the values of the entries could go from 0 to 1, where maybe 0 is completely black, that pixel, and 1 is completely white, or 0 to 255, um, depending on what code you use. Again, I myself, like for example, didn't write the code. Like I just entered it as a prompt, either on GitHub Copilot, even ChatGPT. If you can like ask it to write you the code, it would. But it kind of creates like a fit. I mean, and also you can see here like on the screen if you want. But it kind of like creates like a very simple, like it creates like a very simple code where you enter that, and then yeah, and then it would kind of like output that. Let's see, and then well, how is this? Finally, thank God. Okay, and then you can kind of like run it. So. And now why am I in Greek alphabet? Oh my God. Is this Greek alphabet? Like, what do I have it in Greek? This is so odd. So, okay, this is crazy. Okay, so the file is image to. Oh, if you press tab, just what, like tab, and then it gives you. Okay. Oh my God. So you see, like I don't know anything. So but I swear it worked. Oh, okay, perfect. Okay, so that's like kind of very silly experiment, but because I just wanted you to like it was spitting it out as a 5 by 5, like I kind of like partition it into a 5 by 5 matrix, like the image, and then like every entry is kind of like the value in grayscale, of the corresponding pixel. Of course, you can make a larger matrix, like more rows, more columns. It doesn't have to be square either. And you could add something to it, kind of like ask it to also show you the singular values of the matrix. That would be fun, and that way you can kind of like maybe see as you change the number of pixels in the image, how do the singular values change? I mean, a little bit of experimentation. That's kind of like the idea. I wanted to be a somewhat open-ended, but I know it's relatively straightforward. And again, if someone needs with the code, I'm happy to kind of like share like the one that I got. But it is so easy these days. Like you just write the prompt and it gives it to you. So like it's also it was frustrating for me because I knew nothing. So like, but it's kind of like fun to kind of like try those things on your own as well. So that's like the thing that I was going. So that was the first thing that I was going to show you, kind of like something like that where um you kind of just to like them to generate the matrix. And the other one was like the one that's a little bit more interesting is kind of like the image compression one. And so where you uh input the matrix, and then it's going to kind of like apply an SVD to the, or sorry, you input the image, it will apply an SVD to the matrix that you that it in the algorithm, and then you kind of like choose like the rank that you want the matrix to have, like when you do the compression. Let's check because this kind of like looks a little bit different from what I had. Oh, okay, here it is. So it's better if I just show you. But I mean, I kind of want to give you more details on the assignment. But so you're saying if I just enter tab, no, is it tab? Right arrow? Where is the right arrow? Okay, yes. I'll just type it because, and then I'll just do copy paste after that. Okay. It took me some time because it's doing the compression and everything. But I'll show you in a moment once it's done. Oh, here the k equals 50 means that the rank of the matrix is going to be 50, right? So it's applying an SVD to the matrix and it's keeping the 50 largest singular values. That's what we were discussing before. So let me see I think it takes a couple of seconds. Okay, and then where is I think where's what you said I press where? Okay. It should be, oh yeah, yeah, yeah. And then there you go. Like so well, for those who came, they'll see the compressed version, right? So like this is kind of with like not that this screen is not there, right? So this is kind of like the approximation with rank 50. And like you can kind of like do some experimentation to, see what happens. Yeah, like I don't know why now that I connected because it was also showing me the image before, like right here. But if you kind of like change the rank, you can kind of like see the effect, on the on how it compresses. So, you can kind of like have some fun with that. You could also like maybe ask it to show you the singular values of the image as well. But again, it's just kind of like a warm up so that you get some familiarity with Julia, some very basic thoughts. Like, I mean, again, like it's nothing but of the other world, but like once we go to the tensor networks, once we do some like more like actual problems with that, um, then like the Julia is useful because like yeah, this tensor network library runs better on Julia. So I do want to have like a small mini assignment now for you just to at least have like an excuse to download it and play with it. Let's see. Let's just wait to see if this one is pressed as well. It's faster, like you shift and build it. Oh, like the okay. Reason it's taking so long. Julia has like the first runtime where like if you just give it a fresh code, fine within like time. But if you give it like the function its own, given the record, it compiles it the first one. So the second time it doesn't. Oh, that's interesting. Yeah. Well, I'm glad someone was what they're doing. Very good. Okay, so that's good to know. Yeah, I myself have to play more with it. Like, And okay, and then this is like the new one, right? And you can kind of like see this was I mean, I guess it's saved on the previous one, but it does seem like more less more blurry. Well, anyways, like I don't want to spend. I already lost so much time doing this because like nothing was working today. But I just wanted you to know that the assignment is there. I'll kind of like maybe like I'll let you send you an announcement to remind you that you can try it. And also, there's this very nice book that has like a lot of Python coding. So I posted the first chapter on it on the Canvas side. It's because like we have access to the entire book on the Rutgers library. So if you kind of like goes over the SVD, but if you see here, like it has like some of the code if you wanted to write it on MATLAB or like Python. So you can also use that one as well. So it kind of like does some comparison of like, the region of image versus rank 100, rank 20, rank 5, how much the percentage like compression is, like the storage. And it has like other cool applications that we won't go over because I mean, this is not a course on SVD, right? But we will use SVD for the tensors. That's why I have spent some time on it. But it's like a good chapter to read. It has some applications to face recognition and other things. So it's kind of like a fun thing. If you want to learn a bit more about like the SVD, you can kind of like check out this chapter. It's pretty well, like it's like I think you would be able to understand all of it because it's like a pretty good level of explanation. So it's not too complicated. So yeah, like the PDF is singular value decomposition. Um, okay, let me. Yeah, so like just to go back to like the topics. So the only two things I wanted to maybe the rest of what I wanted to mention regarding the SVD, they're just kind of like faster topics, which are still useful to bring to mention explicitly. So one, which I think I should have enough time today, is just to talk about the pseudo inverse, which is like a useful, it's like a generalization of an inverse to non-rectangular matrices. So it's just kind of like nice to know that there's one. It's like a very useful application. And even square matrices, like like you can talk about the pseudo inverse. So that's a good one. And then I'll give you like an application to probability theory, which will also be convenient for like when we go kind of like on the machine learning algorithms, like when we train something. So no, that one is also going to be nice. But yeah, like I think in the time that I have left, like the pseudo inverse is kind of like a good example to discuss. So okay, so and now I don't know if like the quality of the PDF looks better, but okay. Let me just huh? Okay, so why is the inverse of a matrix? Quick reminder, right? If if A was square matrix, right? Why is the inverse useful, right? Like the inverse is useful. Why is A inverse useful? Well, one of the main reasons is that if you have like a system of equations, right? AX equals B, if the matrix has an inverse, then it's very easy to find a solution because you just multiply by the inverse on both sides, and that just gives you, the solution to the system of equations. So, but like from a perspective of systems of equations, that's why the inverse of a matrix is convenient. Okay. Now, you would like to know what you can do if the matrix is not invertible. What's the next best thing if the matrix is not invertible? So, what to do? So there's a matrix, you can find something that's called like a pseudo inverse or like Moore-Penrose pseudo inverse. So there's a thing called the I'll call it A plus because it's usually kind of like the name that's given to it. So the Penrose-Moore pseudo inverse. The game that it more or less works as the inverse should work in the idea of this. Okay, so let's start with the basics. Let's say that I'll make my matrix A be n by n. Okay, so this is an n by n matrix. So from our perspective, it's useful to think about it as you know, like the perspective of like as a linear map, like a linear transformation. So if you remember, like when the matrix is n by n, kind of like the domain is Rn and it lands somewhere on Rm. So I'm going to try to draw them with different sizes just to kind of like emphasize that they're not square. And this is where like the matrix A goes. Okay. Now the pseudo inverse will go in the opposite way. So the pseudo inverse will be of the opposite size. So this is how it would look. So the pseudo inverse is going to be n by n. So it kind of like flips the signs. Okay.
Normally, going first,
Right.
it's like what we do when there's, I guess it goes zero with,
Yes, that's like how you right. Usually in the matrix work, when you try to find the identity matrix, like one of the algorithms is like you augment it to the identity, you do row operations, right? And you could get to the identity after doing row operations on the what you're left with is like A index, right? Um, right, like that doesn't mean a square case, how you would find it. So what we're doing here is kind of like a generalization of that, of now even when it's not square, right, what should the inverse be? Which is in the same like with what we did with the eigenvalues, right? Like the eigenvalues, strictly speaking, are only for square matrices, but like that's the point of the SVD that it kind of like allows you to extend the idea of eigenvalues to rectangular matrices. And what we do with that means.
um, but if n have a different, like, um, how would you map bigger spaces?
Well, no, like you can always you can always do those mappings. Like for example, I still haven't said what the properties are, right? But like, I mean, here's like a mapping from, has nothing to do, you know, like, for example, think of a projection, right? That maps,
Like, how would you then map smaller to bigger space without like?
well, no, there is something that, you know, it's not going to work perfectly all over, all over the space, right? But like where it's supposed to work nicely, you're going to enforce that it works nicely where it's supposed to work nicely. But what I'm going to say is like, where is it supposed to work nicely? Because I agree, that if the spaces have different dimensions, but even like this is supposed to work even when the matrix is square. So like it's not necessarily something relate. Like you could find a single inverse of a square matrix which is not invertible. So it's not so much about that whether the dimensions have like large, like, the domain and the codomain have like different dimensions, because it would always, you can even find it for like non-variable mean. But it has like but kind of like you'll see like the the definition is kind of like pretty natural once you write it down. Okay, so to kind of like think about what the properties should be of the, to think about what the properties should be of the pseudo inverse, let's go back to the original like relation with between the matrix and the inverse, right? Why was the matrix why was the inverse of a matrix useful? What I was telling you a bit earlier is that the matrix of the inverse of a matrix was useful, especially when you were trying to solve systems of equations. But of course, I mean, you can obviously solve systems of equations even when the matrix is not invertible, right? Like, so remember that so it's kind of like useful to understand first, when is it that like the matrix itself, when is it that the system itself, it can be solved, right? So let's just recall, when is the system solvable? And if you remember, kind of like, there's like a nice interpretation of the solution to a system of equations in terms of like a column space, right? Because there's one way to think about A times X as a linear combination of the columns of the matrix. So A times X equals B can be solved, right? Precisely when B belongs to the column space of A. But Isabel, where does the column space of a matrix live? Uh, in in which of these two boxes does the column space of the matrix live? Which letter did you say? N, you said? Okay, the matrix, right? The matrix is M by M, right? So the matrix is like, let's do it like 2 by 3, right? Like just to make it more concrete. Let's say it's like a 2 by 3 matrix, right? So it would be A11, A12, um, you know, right? So if this is a 2 by 3 matrix, right? So in the picture that we had, right? It actually goes from R3 to R2, right? Because like this has to be operated on a vector with it operates on a vector with 3 entries, right? So, but if you look, the columns themselves have two elements, right? The columns have two elements. So where the elements with 2 columns live is here on the target space. So actually the column space sits in Rm, if that makes sense. Does that make sense? So this is where the column space lives. Yeah, it's always useful to kind of like yeah, kind of like write it down for 2 by 3 to kind of like see more concretely where all the spaces are. And the row space lives here, then, right, like in the first box. So the row space lives here. right? And I don't know if you remember like the fundamental theorem of linear algebra, that there are two more things that you fill this in with. What else? The null spaces, right. So okay, so you think about the null space, right? So the null space of the matrix, what was the null space of A? The null space of A was like the vectors for which A times X equals the zero vector, right? But those vectors, like for example, in this in the concrete example we're talking about, have three entries, right? So the null space actually lives in the same space as the column space. I'm sorry, as a row space, sorry. Like because the null space has our vectors of three entries, so the null space actually lives here. Okay. Right. And this one can be filled in also with the null space, but of the transpose, right? So the null space of the transpose lives here. Is that okay? And then the fundamental theorem, well, I think it is called the fundamental theorem of linear algebra, right? Says that these two spaces are orthogonal, right, to each other, right? So if a vector in the row space is orthogonal to a vector in the null space, and similarly here, a vector in the column space is orthogonal to a vector in the null space of a transport. So they're orthogonal decomposition. So I mean, they don't look orthogonal, the spaces, but they are like, you know, so row and of A and alt null of A are orthogonal spaces. Orthogonal means that, you know, that if you take a vector from the row space, it's perpendicular to a vector of the row of the null space, and similarly with column spaces. Is that making sense? Kind of like, hopefully it brings about, that'd be better now. So, the idea, okay. And it's also useful to kind of like think about again to the original what happens in the case that the matrix A is invertible? What happens in the matrix in the invertible case is that basically the row space and the column space fill out everything. There's no null spaces, right? The null spaces are trivial. So in the invertible case, right, when the matrix is invertible, when A is invertible, like what happens in the invertible case is that literally everything is either, you know, row space or column space, essentially. So all of this is like row space, and all of this is, oops, is column space. So that is essentially what happens when A has an inverse. When, you know, like the row and column spaces fill up everything. Yeah, okay, so making sense. So far so good. Reasonable. This is saying every vector. Uh, right. Yes. Like because it's saying like, you know, where is the inverse related to? Because again, where does the inverse come from? Like the idea that imagine that you had two solutions to a system of equations, right? To the same B, right? If you have two solutions to the same B, you can subtract the equations and then you get that A times x1 minus x2 equals 0, right? And so x1 minus x2 had to belong to the null space. So that gives you a if the solutions are distinct, then that is a non-zero vector in the null space. So basically, that's how the inverse was tied to the uniqueness of solutions to the equations. Because if you had multiple solutions to an equation, then you would be able to kind of like, you know, you can just use something from the null space and that kind of So yeah, so x1 minus x2 is in the null space. So basically, to what you were asking, yeah, if you start with a vector that's non-zero, then the A times that vector would be non-zero in that invariant case. Because if it were zero, it would be in the null space, but the null space is supposed to be trivial for an invariant. So essentially, what that kind of shows you is that what the reason why some matrices don't have inverses is because the null spaces get in the way. The null spaces are like the enemy, kind of like in the having non-zero null spaces is what messes everything up.
So if it wasn't one, then the null space would just combine with the zero.
Correct, right.
So x1 minus x2 would be zero.
Exactly.
Which means that x1 is zero.
Exactly. Yeah.
There's a single element.
Correct, right. Yes. Yes, exactly. And so the pseudo inverse is defined so that it works nicely on the nice spaces. What are the nice spaces? The row and the column spaces. So kind of like the defining property of the pseudo inverse. Okay, so here's like the two properties of the pseudo inverse. So the pseudo inverse by asking the two following properties. Let me just copy paste the picture. Oof. Let me start maybe. I'll make this a little bit bigger. So basically, the idea is that if you started with a vector v that's in the column space, but maybe I should. Sorry, before I say this, maybe I should also mention this, which is kind of like maybe silly, but that's kind of like the idea of an inverse. Let's put the inverse picture here. In the case that A is invertible, what is the point? If A is invertible, if you do, if you start with an x, that gives you A times x, right? And then if you apply A inverse to this one, right? That gives you A inverse of A times x, right? But A inverse times A just is the identity, so it just gives you x, right? So kind of like the idea is that it's kind of like kind of like a reversible cycle, where if you start with x, you go to ax, and then when you go backwards to the inverse, you get to where you started, right? So it's kind of like a loop. It just begins when you start. And it kind of like you can start that like anywhere, right? So kind of like the same is if you started with something like with b, if you started with a vector b, right? If you started with a vector b, you can kind of use A inverse, right? That gives you a vector A inverse times b, right? And then you can apply the matrix A to it, right? And then you find that A times A inverse V equals B, right? Which is, so it doesn't matter whether you started with an X or with a B, when you brought it in the cycle of A inverse A or A inverse, like it kind of like you start with it goes back to where you started. Okay. And so basically the pseudo inverse is constructed so that that continues to happen, but with the condition that the vectors you chose were in the row or column spaces. So it's kind of like just ignore the null spaces because those are the bad places. So you just ask the same property to kind of like work in the in the in the column spaces. So for example, maybe actually let's start with the conditions. So the first condition is that if you start with a vector that's in the row space, let's call this vector X. If you start with a vector that's in the row space, and then kind of like here you get 8 times X. I don't want to be biased, so I'll just put it somewhere. If you get 8 times X, but then you hit it with the pseudo inverse, right? Then the pseudo inverse should give you back what you started. So this is a plus, okay?
So that includes A X is in the all of it.
Uh, right, like yes, I'm not right. I'm not saying where it would land. So it could have landed potentially. That's why I'm putting it kind of like outside the two boxes to not be biased on whether it should be landing.
But the two vectors are the only thing that are.
In the sense that everything is a linear combination of something from here and something from there. Yes. Like they span entire Rn, right? It's a vector space, so right, it's not like the x-axis and the y-axis. So everything is a combination of the x-axis and the y-axis, but it's not like a union. Right. That's the difference with vector spaces.
Isn't the null space like a space itself? So like the null space plus the column space of a gives up
Right, but the plus, all that I'm saying is that the plus in the sense that, right,
like the unit.
well, that's the point, right? Like, when everything on Rm, right? Every vector on Rm is a linear combination from something in here plus something in here, right? But it's not that it's in either of those, right? It's a span, not a union, actually. Like that's the thing with linear algebra, right? We don't have unions of sets. I mean, unions of sets are not as interesting as the span. So, the null space could kind of like be, for example, the x-axis, and the column space would be the y-axis. So it's not that everything's either on the x-axis or the y-axis. It's more that everything is a combination of something with the x-axis and the y-axis. Is that making sense? Yeah. We're doing that.
If you put a vector into A, goes into the row space, it'd be zero. Right? So how do you reverse zero?
Wait, isn't there two null spaces here, right? There are two null spaces here.
Yeah.
So if I start with a vector x, right? If I start with a vector x, I'm doing A times x, right? The only place where, right, but here, this x, I am choosing it in the row space. That is like, that's the starting point. Like for this one, it's guaranteed to be in this particular box, right? So this one, like, the way I chose it, this one is not going to be in null of A. You see what I mean? Unless it were the zero vector, because the zero vector is kind of like the only one that's kind of like in both at the same time, because the zero vector is the only vector that's orthogonal to itself. Right. So there's okay, this picture is not 100% accurate because there's kind of like a vertex that they both share, which is the zero vector. If you want to put them kind of like, so, you know, but except for that, like they are disjoint in the sense that there's no one that lives simultaneously in both boxes, right? So by writing it this way, that's why I'm saying here if x is in the row space. So I am saying that this one definitely will be in the row space, but I'm not claiming anything about where A times x is going to land, right? So A times x just lands somewhere on Rn, but you want the pseudo inverse to kind of like reverse the operation so that if you apply the pseudo inverse there, it will give you back the x, which is kind of like so it's kind of like inverted. It's kind of like the cancellation property because it's almost saying like that a plus times a is like the identity, but it's saying, oh, I don't want that to be necessarily true everywhere. I just want it to be true if you had fed something from the row space to the matrix. It's a little bit more like,
But isn't that like technically, there's high definition visual?
well, it is the original inverse does have that property, right? The only difference is that in the vertical case, again, like
There are some.
the null spaces do shrink to a point. So they just fill up everything else, like the row and the column spaces. So it's not, all that I'm saying is that kind of like the pseudo inverse is the same as the inverse, but on the nice spaces being the row and the column spaces. Yeah, that's not what they, yeah. It's very natural when you think about it, but you have to.
So we're just extending definition. Or.
Right.
Wise, logic.
Yeah, exactly. It's kind of like, it's supposed to work as an inverse in the places where you would like it to work as an inverse. It's kind of like the idea. And then the other condition is kind of like the same, but where if you had started with something from the column space. So the other condition, like let me copy paste the picture as well. The other condition is kind of like similar, where if you ooh, what a mess. But the idea is that if you had started with, actually, let me I may do it again. Yeah, let's just, I take it back. I don't, okay. The other condition is kind of like the same, where if you start, if you get started with something in the column space, like let me put Rn, here's Rm. So you start now with a vector in the column space. And again, here you have the null space of A transpose. And then you have row of A, null of A. So again, you can hit it. You can apply the pseudo inverse. I don't know where it's going to land. Again, I'm being agnostic of where it should land. So I just put it there. So that's A plus of B. Okay, so this is A plus B. But the idea is that if you hit it with the inverse with A, it kind of like reverse to where you started. So if you hit it with A, if you do A to that, then A of A plus B should be B. If B happens to be in the column, that's kind of what we're doing. So it's kind of like, yeah, the closest thing that you could ask for an inverse, like, it's an inverse where you would like there to be an inverse. That's kind of like the idea, like, so it's like a very, if B happens to be in column space. So those are kind of like the two, this like, conditions that you're after. And then the other one is like this one. Yeah.
You're like, that's fine. Just like somehow related to like that same fantasy. Extract or real value from them. In terms, just extract the real value. Forgetting about that crap.
Well, I mean, it doesn't,
That's really good.
there's not a direct relation just because like, one is like an infinite series, but it is kind of like, to the extent that it's related, kind of like, what can you salvage, like what can you save from the previous construction, then yes, but that's kind of like in mathematics, how most things are done when you're like extending the definition. What can you save from the past, which is kind of like the tensor rank, right? The tensor rank that like the matrix rank has tons of different definitions, right? There's kind of like 10 equivalent definitions of like the rank of a matrix. Let me say one of those, and I will call that the tensor rank, because the idea is that most of them don't really work that well in the tensor case, and it's kind of like similar here. There's a lot of characterizations of the inverse of a matrix. Let me kind of like collect the useful facts about the inverse and just save those facts, and that I will ask for the pseudo inverse at the expense that, yeah, certain things are kind of like sacrificed. So obviously it won't have the same properties as the inverse, because the inverse is kind of like the ideal goal. But this is what is the next best thing, that you can do. And so, for example, and like maybe before the cool thing is that I mean I still have time to write it down. The cool thing is that there's like a super easy way to find the pseudo inverse once you have the SVD. That's why it's related to the SVD. What I want before saying that, maybe just let me write two things. So two things. So again, if the idea is that when A has an inverse, when A is invertible, the solution to AX equals B has solution X equals A inverse V, right? And the idea is that when B is in the columns, okay, now if A is not invertible, right? The next best thing to solve what you need for solving a system of equations is, that B is in the column space. So when B is in column space, a solution to AX equals B is X equals the pseudo inverse times B. So kind of like the idea is that, you can find a solution kind of like almost in the same way, using the pseudo inverse instead of like that inverse. And let me write one example of a 2x2 case so that you see it's kind of like, this is like a very simple example. So for example, here's an invertible matrix, the easiest one in the world. This one is invertible, right? Because like the determinant is just 6, it's not 0. So the A inverse is just, because it's diagonal, literally A inverse is 1/2, 0, 0, 1/3. So it just really corresponds to inverting the numbers along the diagonal. In the case of a pseudo inverse, like, so for example, if you had something like diagonal, so see, for example, this one has no inverse, right? Because the determinant now is 0, but the pseudo inverse in this case is like 1/2, 0, 0, 0. So it tried to invert what it could, so it kind of like some makes that feeling that, it's doing its best to invert things, it just takes away, it stays away from converting like zeros, because it cannot. But and so and the idea is that you can find the pseudo. I mean, I'll just kind of like write it as a statement because I'm not so interested in the proof. It's just kind of like, and just to show you that the SVD has all other uses. But the idea is that if you can find, so this is what I wanted to mention for today. The key fact is that you can find A plus from the SVD decomposition. So just to remind you, what is the SVD? Okay, the SVD was, you have a matrix A, and you write it as U sigma V transpose, right? So A again was n by n. U was U and M, U and V are square matrices. Okay. And then this one is like n by n. And the one in the middle is the one that has like the singular value. it's not quite diagonal, but you can like put the singular values along the main diagonal in quotes. So for example, like sigma could be something like, let me put like an example of like a matrix sigma. Where do I have it? Okay, sigma could be something like sigma 1, 0, 0, 0, 0, sigma 2, 0, 0, 0, 0, 0, 0. Okay. So it had like it was mostly zero, right? But it has like the similar value, right? I guess.
But technically, since sigma is literally just a diagonal matrix.
Yeah, right. Because it may not be square.
Right.
Yeah.
But in U and V are square matrices, so by definition, they should have. Right, they should have.
Well, U and V, they're not only square matrices, but they're also
Eigenvectors too.
right. Like they are no, it's even better than that because they were orthonormal basis of eigenvectors. So they are like rotation, like they're orthogonal matrices, meaning that they're like rotations. So they are complete, like they were invertible. U and V were invertible matrices.
Okay, right, so since they weren't vertical. Are stable. Or is it literally just take eight first of you guys know and then.
Well, that's basically it. Yeah, that is basically it. Yeah.
Oh,
Yeah. I mean, but you just have to check. You just have to be careful because of the sizes, right? So you just have to play with the sizes. But yeah. But that is more or less like the idea. So
and we got to derive factors.
yeah, it's just like the non-invertibility is coming from the middle piece, right? Sigma. So you basically invert sigma to as much as you can by doing 1/sigma 1, 1/sigma 2. You do have to transpose it because it may not be square, right? So remember, like the pseudo inverse goes the other way. So you transpose it and invert the non-zero. Like actually, let me write that first. So in this case, like sigma plus would be, it's what you expect it to be, but you just have to, flip it because of the not being like a square matrix. Right? But yeah, it's very intuitive. You see, that's the point of the SVD. It's almost basically obvious what the answer should be. And then you just have to, you have to be careful with the fact that, like if all of this could be invertible, right? What would be, let's pretend for a moment, maybe this is like the easiest way to kind of like see what the formula is. Pretend for a moment that you could invert everything, right? If everything could be inverted, and then you kind of like just fix it in the obvious way. Could be inverted. What is A inverse? So I don't know if you remember the inverse kind of like changes the order in which the factors appears, right? So you get V transpose inverse, sigma inverse, U inverse, right? Is that making sense? But these are U and V are orthogonal matrices. That means that their transpose are their inverse. Like that's one a property of an orthogonal matrix. So V transpose is V inverse actually. So this would be V inverse sigma to the -1, and then U inverse is U transpose, because like I'm just using here that U and V are orthogonal. No, a matrix is
I tried that.
a matrix is orthogonal. Sorry, a matrix is orthogonal. As an aside, a matrix is orthogonal, meaning that the column vectors are orthogonal of the matrix.
All like also like if there's like so each column vector.
If you graph an orthonormal, yes, like because of the identity, right.
So it's 3 by 3.
An orthonormal basis of R3. Well, not necessarily E1 in 2 3 because you can have E1 in 2 3 and you do a rotation and that's still like an orthonormal basis.
But like that would be an example.
Right. In fact, kind of like it's kind of like group theory because that's what this corresponds to, but almost basically every 3 by 3 matrix is kind of like which is orthogonal if you have determinant one is like a rotation about an axis. That's Euler's theorem. Which is used in basic dynamics, I think. It's like a fun theorem to prove.
Take that.
I mean, it's I mean, it visually is plausible, but you know, it has to be proved. Yeah, but it's kind of like you should think about it kind of like as some sort of like rotation. But well, what that means is that okay, so all that I'm saying is that in this case, you end up getting after this small aside, if everything were invertible, then this would be V sigma inverse U transpose, right? That's what you would get if everything were invertible. I mean, we do know this. The factors of the first and third factors are invertible. The only one that's problematic is sigma inverse, but then just replace it with sigma plus, like the way I told you, and that's it. That is the pseudo inverse. So in the general case, it is the same formula, and which again, it's very plausible if you think about it from that perspective. Is A plus is just V sigma plus and you transpose, and that's it. So it's kind of like the best. It's kind of like goes to this analogy. What's the best thing you can do? Just invert the non-singular values that you have, and that is the sigma plus, and that's it.
I guess we kind of assume before the like just take the inverse, go on, go back, coming on. The one example, so like 2, 0, 0, 0, just assume that it would work. Like, I guess it's like a sort of larger.
Well, I mean, like it. I mean, just put
Yeah, like the signal plus.
right. I mean,
How do we know for sure?
I mean, you just have to think about like you know, like the properties that I asked for,
Oh, okay.
and it's super easy to kind of like for something like this, since it's overwhelmingly zeros, it's kind of very easy to understand what the kernel, you know, what the null space is. You know, you have to understand like, oh, when would this be inverted? What would you expect this to? Where is the column space? Where is the row space? It's very easy to find the row or column spaces. You know, these are the only no. You know, for example, these are the only non-to-zero values, right? So what is the row space? Like the first two rows of the matrix. What is the you know, like it's kind of like all very explicit because there's almost no row reduction needed.
And as a reminder, sigma is a diagonal
Well,
all the time.
it's not diagonal in the strict sense of the word because it's not.
I mean, yeah.
Yeah. Right. It's mostly zeros except the singular value, right? It's
Yeah,
zero
like
except
only at like I equals J.
right, yeah. And right, so it's filled with which one to sorry. So it's filled with overwhelmingly zeros, right. And sigma plus is kind of like inverting it, but you also have to switch the sizes, transpose it because you know again the matrices are not square necessarily. Um yes.
I guess if you scroll up to your example or something, A plus, would it be more fair for the matrix to plus use like 0, 0?
Like infinity here?
Yeah.
But you cannot have like any well, but I mean you cannot have like entity infinity, right? I mean it's just more like remember like you don't want anything like kind of like the idea is like you don't want it to I mean it's in the null spaces there's almost nothing to worry about because like you want that kind of like in the null spaces to like to just go to zero basically like
Yeah.
like so that's why like you would put zero here.
Yeah, it'll always like okay, it always works.
Yeah.
Like X A.
Well, right. Like, in this case, it's very again. It's kind of like very easy. Like you know, what is the row space? The row space is just 2, 0, and what is the column space? It's like 2 zeros. Like you know, you just want it to be invertible in that place, and to invert it, you just have to
Oh.
reciprocate. Like you know, because reciprocal of the number.
Yeah. Only the it's basically selecting the first.
Yeah. Right. Exactly.
So you just invert it.
Right. Inverting it there. Yeah.
Okay. That's what.
Right. Okay, but again, like, and by the way, this is also related to least squares method. Like, maybe just to finish for today. So there's like a relation with least squares where, so this pseudo inverse is you will see it if you take numerical analysis or something like that, even if they don't call it that. So, but the idea is like, you know, if a times x, you know, what if a times x can be solved? You know, that can happen. That will happen whenever D is not in the column space, right? So kind of like the idea is that you have the column space And then you have the vector B. Right, and the way I'm drawing it, B is not in the column space, right? Because I think it's just outside of it. So you could try to find, you could try to find where is which is the vector, let me call it Y, so to not be biased. So which is the vector in the column space closest to B? Kind of like, in the sense that it minimizes the distance, this vector is kind of like has the least distance to B. Like that's why it's called least square, because we look at the distance formula, it involves, the Pythagoras theorem, it involves like squares. So and so the idea is that the vector Y is A of, wait, it would be a, well, no, I mean, right, it's with the transpose, but but the pseudo inverse is kind of like a generalization of like that situation. So it is a projection, but right, like, but the formula is that the idea is that the formula can be given in terms of like the, uh, yeah. Like what I'm trying to say is that it's yes, this is the pseudo inverse. Like, I mean, not the pseudo, it's A of A plus of B. That's kind of like the idea. But right, like maybe just to connect it to what you just said, the idea is that if, as another remark, if A transpose A is invertible, is that the one that I want, then the pseudo inverse is something like, yeah, like so in these works, usually you have that assumption that that happens when the matrix A has to rank or something like that. But I'm just saying, like, this is kind of like it's like a more, in more generality, you can use as the decomposition to define A plus, even if this is not full. Okay, this is a good place to end. Sorry, I went over time, but it's just trying to make this like setting up of the assignment work was a bit more frustrating.
It's got, A times A,
Okay. Maybe it's like a picture here, right? Like what I'm saying is that
shouldn't Y be pseudo inverse times B instead of A times B pseudo?
okay, so the idea is that you have A here, right? Here's where B lives, right?
So
You I'm not putting right. That's why I'm not putting it anywhere. Like, and that's why I dropped the column and the null spaces. Let's just have like somewhere randomly. You apply A plus to it, right? So this gives you X equals A plus of B, right? And then you keep this with A.
That would only work if we use
Well, let's see. Where is? Let's go back to the picture. Yeah, it can be confusing. The column space is on the right side. Right. So I'm just saying, if now let's say that the B is not in the column space, because if B is in the column space, then the solution, it was just like the pseudo inverse. All that I'm saying is that this kind of like kind of like the least squared solution continues to kind of like work in the same way, where maybe you have a B in a random spot.
let's say B,
Right. It's a combination of something in the column space and the null space or whatever. You hit it with A plus, that gives you something, right? Leave something that is kind of like an X value. You hit it with A again, and so that gives you, A of A plus B. And all that I'm saying is that this vector, whatever it is the closest in Pythagorean distance to the vector B.
And that A plus B is columns.
Yeah, that is, but because it's A of something, so that makes it in the columns.
When you do A plus B, where is that vector go? What space is that?
When you do A plus B,
Yeah.
I mean, in general, I mean, you can like, look at it from like SVD, but yeah, I guess in general, like, it will just like land somewhere, like, it could be, I guess, in general, like a combination of the, it would be a combination of the row space and the null space, right? But it may, I don't think in general you would say that it's either on one of those, right? But it doesn't matter because it's just like an input that you can use. So you can apply the matrix A to. Okay. All that I'm saying is that, okay, you start with a B. It's not necessarily in the column.
What if we assume that B just purely in null space?
Okay, right. Okay. It is B is purely in the null space, right?
Right, like in the sun, the plane is the top space. Vector.
Oh, okay, so let me make the picture a bit better. So,
No, some of the 3D.
oh, what 3D?
Yeah.
Okay.
Yeah,
You have the column space, right?
yeah,
If you have a vector B, which is not necessarily in the column space, right?
yeah.
Right? The thing is like if B is in the null space is perpendicular to the column space, right? So like the solution would just be zero. That's why I make it kind of like slanted because otherwise it's too simple. You know what I mean? It's kind of like better to think that it has like a contribution in both directions. So you're trying to find the vector Y.
The linear combination.
Right. And or something orthogonal to the null space, right? Yeah. Sorry, something orthogonal to the column space. So you're trying to find the vector Y that's closest to this one,
Yeah.
right? So what I'm saying is that that's called the least squared method problem. Like that's what least squares is about.
Yeah.
And you can set it as a Calc3 problem actually, because you have a distance function and like minimize the distance. Like set partial derivatives equal to 0. Actually, but all that I'm saying is that there's like a very elegant solution with the pseudo inverse, which is you have a random B, you don't know where it is, right? You go with A plus, now you live in the input space, right? So that is some sort of X, and then you hit it with A, and when you hit it with A, it is A of something, so that makes it in the column space. And kind of like the point is that you can show that that is the closest one to B. That's what I'm trying to say. Sorry, what do you mean?
So if you select B to be purely in the null space, that means its projection in the column space must be 0.
Right.
Which means the pseudo inverse times B would be in the null space of A, which then
Right.
by A will give you 0.
Exactly. Yes. Good. Very good. Yeah.
It's a muscle functions, but H transpose A, it's like that. I'm sure I really
Right.
all ones with all of that's great first power all the time.
Yeah. Right. Yeah, in those cases, it's very natural to that A transpose times A will be vertical because that's not like but like that's like a very practical assumption. I mean,
How this is so stupid.
well, you have to check. I mean, it's kind of again like if that happens, you do check that the pseudo inverse gives you what you wanted. And then from the SVD, you would just have to check. I mean, the thing is that you use like the SVD formula for the pseudo inverse to see that it has like the right property, or like for the minimization problem. But I don't, that is why it's not too bad to double check, But it's not, the point is that this formula, like this formula that I wrote, it doesn't use anything of whether A transpose A is invertible or not, right?
Yeah, I guess I was wondering why can you like generalize like you have the formula A and this B sigma and this how can you like just jump to say that A plus to just replace the
Well, I mean, I was doing what you would call like a heuristic argument, right? I meant that if in the ideal world, when everything is invertible, that is the formula, right?
Yeah.
And you would like A plus to agree with A inverse, right? You know, like A plus and A inverse should be the same whenever that's possible, right? So this is the formula that works in the ideal world. But you notice that these two terms do make sense all the time, right? So it's just the question of like what should you replace sigma inverse with, and then you come up with sigma plus, and I agree that that's not a proof, but it's kind of like a plausibility argument, right? Like if you had to generalize, like you would bet on this. If you have to make a bet, oh, let me try to prove that something works. This is like the one you would try to prove that works, right? But then you do have to prove that that has like the properties, but it's not too hard to prove the properties because U and B are orthogonal matrices, so you can kind of like check. Yeah. Right, yeah. Yeah, it's like a bit tedious, I suppose, but it's kind of like plausible, you know what I mean?
Yeah. Oh, okay. That makes sense then.
Somewhere,
So, sorry, I just wanted to like to reflector on, so the SVD thing that we
Mhm.
do, we get an orthogonal matrix times a diagonal.
Let's say diagonal.
Diagonal matrix
Right.
and another orthogonal.
Yeah, right.
And isn't that something that we also get when we diagonalize the square matrix?
No, because with the square matrix, it's P matrix, like when you diagonalize a matrix, it is P D P inverse. So they're not necessarily rotation matrices. They're not like they may not preserve, P and P inverse.
Isn't P also P and P inverse honestly not?
No, they're not orthogonal. Like they're not
For a general diagonalizable matrix.
I see.
You diagonalize.
right.
I see. Well, considering that P is an orthogonal matrix, if we happen to have P to be an orthogonal, then this is just P transpose.
Right, and then that means that A was symmetric.
Oh, yes.
Yeah, so you cannot get away from that. Right. If P happens to be orthogonal, then you can replace this with P transpose, and then that forces A to be symmetric.
I see.
So that's why.
Is that true for any symmetric?
I mean, every symmetric matrix, that's not what the spectral theorem says. Every symmetric matrix is this way. Yeah.
Well, then in the case of symmetric matrix, does SVD give us this?
It agrees if you right. Actually, that's one of the assignment problems. How does SVD look for? I mean, I haven't made it I haven't officially said to do it, but yeah, in SV, basically for symmetric matrices, SVD is more or less already what you already had. Like you just have to be a bit clever.
I would place my bets that this is exactly what SVD.
I mean, it may be up to because I think you have to split like the.
You're pretty negative.
Right, you have to be careful with that because remember, like the singular values are the absolute values of. Yeah. But it's almost that. Like there's not like a big.
Because it's the modular.
If you're a symmetric, you might as well just use the spectral theorem decomposition. Like like if you wanted to, that's great. But SVD is really great outside the symmetric matrices are the best matrices. More or less, and orthogonal ones. Like those are like the two best matrices you could be. So you're already good to go. You don't have to worry about those, right? And SVD is more or less the spectral theorem, in quote, like up to like the sign stuff that you're saying with the eigenvalues. So it's really this is only interesting outside the symmetric world, like that's one way to think about it. Yeah, but one of the assignments will be about that actually. Yes.
Okay, so I guess like the one thing
Oh, my sorry.
How can we claim that like AX is gonna be in that house? It's like, how can we say that A plus B, that A plus B, that generates our X? How do we know that generated X with A has to
Oh,
be the
but it just means like what's the definition? How do you find A times X? A times X is just x1 column 1 plus x2 column 2 plus xn column n. So that automatically makes it a linear combination of the columns of A.
Yeah.
So
Yeah.
right. So if you
Like, the X generated from A plus B won't send you to the null space.
well, but I mean, but the thing is like again, like the only place where the null space and the column space agree is at the zero vector. it's what I was saying earlier, like, they're not quite disjoint, but they do share the zero vector. So but you cannot like, I mean, that's what the fundamental theorem of linear algebra says, that these two vector spaces are orthogonal. So you cannot be simultaneously in both unless.
No, I know what you mean. What I'm saying is, you have your vector that you get, you from A plus something.
Okay.
And you get a solution X.
But no, it's not a solution. It's just a vector X. It's not.
Vector.
Right.
Vector X would be your B, which is mixed between column and null space.
I think you're getting confused.
No, it's not. It's gonna be row space and the null space.
Right. Like here's where the.
Row space of A, or the null space of A. A of that vector will either be in the column space of A or the zero vector.
Is that there are two null spaces? That's what's confusing you. Also, I feel.
So then X has, it's impossible for the X generated from, if B was initially a column space and a null space, then the X generator has to also be the row space.
If B were original in the column space and the null space, then B is the zero vector. Because the only vector that's in both is zero vector. What were you going to say? Sorry.
I think, right, I think the X. Yeah, I think everything we can do, when we're hard that X. Yeah.
This X, right? When I write this X, I'm not saying that this X is in the row space or the null space. It's just somewhere. But it just needs to be somewhere, because the moment it's somewhere, A times X will be in the column space. That's automatic.
Well, yeah, but that equation says X equals A plus.
Oh, right. This equation says that X equals A plus B. Yes. Right.
That, well, yeah, for that to. So for that. For that X to be.
But
A plus here is called like a pseudo.
A plus is called the pseudo inverse, right? A plus is the pseudo inverse. Well, but to your question, right?
It's not A plus. So you're saying like a B can't be zero.
Well, I mean, it could be zero, but then that's not true.
Right.
Okay, so then A plus B. So X, that would never be in null A.
I mean, like
It has to, no, that's, if X equals A plus the inverse is a, no, not the
Yeah,
inverse.
if this happens to land in null of A, then the moment you do A, right, that would kill it, and that means that B was zero, right?
But you're running X outside, like, I guess X in this picture is outside of the row space and null space.
Right, yeah.
It really should be in the row.
That
It
doesn't
should always be in the row space.
It should always be in the row space. Well,
if B is
I don't think so, because like, I mean,
if B is purely in the null space, then its projection in the column space is zero, which
It has
is
to be in the image of
A.
it has to be in the image of A plus.
right, but that's not the row space of A, right? I mean, that's not. I mean, I guess A plus is not the same as A transpose, right? So like, row space is not column. I mean, row of A is columns. I mean,
It's not the same, but I think.
maybe
It's not the same
they.
image because it's going from.
I mean, that could be true. I guess I have to double check it, but yeah.
It's going, it's just. Yeah, it's.
I mean,
If you, yeah.
it's possible, right? But
Yeah.
did you?
I mean, it's B. It's also the.
But you don't need to know that, right? Yeah, right. Like,
Yeah, it is, because it's also the image of view.
right.
Which is. Gonna be, which is, yeah, those columns that make up the. Which are, when you view, those are the.
Oh, right. If you're looking at it from the perspective of the singular value decomposition, right? Like
Yeah.
that. Yeah. If you do, I see what you're saying. I mean, then yeah, like yeah.
So yeah, like, I mean, yeah, X.
Right.
Really, yeah.
Thank you so
So
much.
picture X.
I should have put it in the row space. That's
Yeah.
what you're saying. Yeah, but even then, like, right, but yeah, I guess that makes sense for the SVD. But the way,
Like, but I guess we started with an AX equals B.
Right.
And that was, and in that case, X is understood to be a general vector.
Right. That's why I wanted
I
to,
guess that's what.
yeah, that's what, right, like, that's, yeah.
Could I get the notes for like the seventh lecture?
Well, again, like, the thing is, like, I never wrote that, I mean, you can take a picture,